Thank you all for joining us for the inaugural Texas FIRST Robotics Competition workshop, hosted by FIRST RGV. A little bit about us, and then we will turn it over to our presenters today. FIRST RGV is a nonprofit founded in 2015 that supports the FIRST community in the Rio Grande Valley, which is an area approximately 3 hours long by 2 hours wide, sits next to the border of Mexico. Yes, in Texas, it's easier to measure by driving hours than miles, just because Texas is just large. Since 2015, we have seen explosive growth of teams in our FIRST LEGO League and FIRST Tech Challenge program, but our growth in the FIRST Robotics Competition program is positive, but we are not where we need to be on ensuring access to the more than 250,000 students in the K through 12 space here in the Valley. With our events like this, we are doing our part to create awareness of our efforts and the need for strong sponsors and mentors to help our community. We are proud Texans, and I'm honored to be part of the FIRST in Texas Robotics Territory. Our organization is proud to be hosting this weekend's event. If we have any technical issues, please remain patient. We will get them resolved as quickly as possible. While you're engaging in the chat, asking questions, and saying hi to your neighboring team, or maybe a team across Texas, we ask that you remain on topic and know that this session is being recorded for teams to take advantage of this great information later. We will post this information on the FIRST RGV YouTube channel, and you can access it directly by visiting youtube.firstrgv.org or by searching for FIRST RGV on YouTube. I want to personally thank the FIRST Robotics Competition teams across Texas that have come together this weekend to make this live event possible, and for the hard work of our FIRST senior mentors and AmeriCorps Vistas across Texas that stand ready to help support our teams. On behalf of FIRST RGV, we hope everyone has remained safe during this pandemic, and we are confident that all of the partners across Texas will be getting ready to bring you a robotics season soon. Thank you.
Hi, everyone. I'm Miles Hernandez, and what I've got here today is the FRC Java programming for beginners. I'm from Team 3035 Droid Rage, and I actually made this pre-recorded video talking about everything that I want to go over when it comes to this topic. So I'll just let myself take it away. I wonder if it's because I'm muted. Let's try that. I'm an alumni, formerly head programmer at Team 3035 Droid Rage. I hope that this semester will be helpful for people from any walk of life with any level of experience. You might consider text-based programming to be obtuse or complex, and in some ways it can be. But we thankfully live in an era where we're able to more easily solve the problems that we encounter as programmers or as any position in robotics or shoot life. We hope to cover that in the seminar. But hey, maybe you'd like some more background on my team or about the programmers. So let's start with that. So let's talk about where my team needs to be at. Don't be fooled, I'm no whiz with code, and Droid Rage has certainly come a long way since its founding. Over 10 years ago, I think. We've been lucky enough to have an amazing supervisor that's kept us in business, but when it comes to adult mentors, particularly with FRC, we've been flying solo for as long as I've been in the program. We're very much student run, and that comes with its own set of pros and cons. It wasn't until about my sophomore year that we really leveled up in many different ways, one of which was programming. I had experience in Java programming from FTC, which I think helped me a lot when I started grappling with FRC programming. The details make them distinct, but broad strokes, both FTC and FRC programmings, they seek to do the same thing. So if you have any experience doing that, then maybe you'll have an easier time getting into FRC programming. I think an important thing to consider is that the way our team programs is a reflection on how we plan out our seasons. This will come up multiple times as I discuss this, but basically, we always try to be utilitarian about our programming. Our code ain't fancy, it's not superb, but the time we gave ourselves to iterate and practice new things, I think it got the job done. And they did very much. We were actually, I think during the first launch season, I have the handkerchief, I think, of that season up on my wall. We made it all the way to Worlds. We were state champions in Texas. And during one of the events beforehand, we actually got an autonomous award. So, I mean, if I had any kind of credibility, I guess that would be where I'd get it from. But hey, that's enough about me, and that's enough about my awesome team. Let's figure out how to program. So what we're going to do is start this off by showing you what a programmer does, what the general programming process is, and some helpful tips, big picture. So let's talk about goals. A programmer in FRC has a deceptively simple goal. Make the robot controllable during the teleoperated phase of a match, and if you have time, make the robot control itself during the 30-second autonomous period to perform tasks for bonus points before teleop starts. I say this is deceptively simple because as you're iterating and creating the code with the sole purpose of fulfilling those goals, you'll run into snags that complicate but ultimately improve your final program. The drivers can't see what they're doing as they go further down the field. They'll have to attach and program a webcam such that the video's large enough for them to see, but still runs at a smooth enough frame rate for them to understand what's going on. You want to start on autonomous, but your drivers want some tweaks to the controls. The intake and outtake commands for the motors work, but the intake wheels are weird, so your drivers want an extra button that's, slowly turns the wheels to make sure the power cube is in the intake. However, as you find your groove in programming, the web that binds all facets of your code may become clear, and you can use that to create solutions for other problems very simply. Let's find an example. Your driver wants a button in teleop that turns the robot 90 degrees. Well, I can just, for instance, repurpose the code that I had already made for turning during autonomous. And I can just use basically that same code, and then boom, I have a button that I can just push in teleop and the robot turns 90 degrees without fail. It's those kind of things. And it's honestly one of my favorite things to do as a programmer, was to have the one thing I learned help me with multiple different problems and tasks. It's like a game of Tetris, and you hit that perfect line block. I think they're called heroes. Anyway, so let's talk about what's in a program. And generally, a program goes like this. You start by creating objects that represent the parts of your robot. Java and also C++ are considered object-oriented programming languages. In order to make your computer, or in our case a robot, do something, you have to create every part of that something in code. you set parameters about what your robot can or can't do. This is important for multiple reasons. For instance, your motors are limited in the percentage of their power. You can't make them run at like 200% power. So you have to write in code that you can't. The program doesn't know otherwise. A big part of the program, and my personal favorite, is the TeleOp portion. You map commands to the controller. You get a lot of freedom in FRC about what you can use to control your robot. Logitech controllers, Xbox controllers, Switch controllers, I think. They're wired. I think I even saw someone use a Guitar Hero controller to control the robot. Shoot. And you can even use like an airplane stick in order to like you can use like a crane. You ever see those crane things in the arcade? I always wanted to use those, but I never got to because my drivers, they're too used to FTC controllers, and they were limited to like just using like the regular game pads. So we never got to experiment much with them. That's a shame. Anyway, this is where I feel your creativity can really flourish in TeleOp, as there are a couple of ways to make the robot do the same thing. And I think it's a pretty fun puzzle game trying to figure out, okay, well, I already know how to do this. Maybe I can use that information to solve this other problem. Plus, you get to communicate with your team and have an active part in the testing process, tweaking the controls, making sure that they're perfectly like souped up, ready, and able to like perform at the best of their capacity. When it's a late night and you guys are testing out your shooter, you really feel like you're a great, important member of the team. And I love that a lot, especially because I was never much of an engineer growing up, but I mean, by programming, I was able to be like right up there in the front lines with the rest of the engineers. That was part of my favorite part. That was one of my favorite memories about the team. The autonomous portion. It runs at the beginning of the match for a short 30 seconds. It's not much, but you'd be surprised how much you can do within that amount of time. We never really got to be wizards with auto, but you don't need to be much. You need to be that for much of the season. A simple program where you drive straight, you gotta have at least that, I feel like. You usually get points just for doing that. There's like a line on the field, and if you cross that line, you get points. Just don't go too far, else you'll go into the opponent's side of the field and, back during Operation Deep Space, I'm pretty sure our autonomous was literally just drive straight, turn 90 degrees, shoot ball, and that program carried us all the way to Worlds. If it's consistent, who cares, right? We actually got an autonomous award during our first competition. It was because we were like one of the only ones that actually made an autonomous. Of course, that year was the only one where you could actually control the robot during the autonomous section. They had like this thing going on where you would have like these screens go over the pilot area, so no one could see, but they could still like control the robot. But we were the only ones that said, okay, well, that's cool and all, but we still want to get autonomous points, and so we did. We want to do the autonomous points autonomously, I guess. That's a funny way of saying it. Let's see. Autos are important. I should have bolded that, should have underlined that, I should have highlighted that, should have everything that. I think cooperation with your engineers to make sure that your autonomous tasks are very simple and you don't have to do a lot of moving around the components during autonomous in order to do tasks, that helps a lot. Just making everything very simple, But that's enough about like that. What do you actually need to get started? Let's be practical, guys. We got only 50 minutes, right? So let's talk about the required tools. In FTC, all you need to program is anything with internet that can connect to two phones. But in FRC, it's a little different. Unfortunately, at least right now, as far as I know, you can't quite swing using something like a Chromebook to program. You need a computer that can both install third-party programs and can feasibly run them. Also, it has to be a laptop since it also houses the driver station application that can plug into the field management system on the field. You put your computer next to it, you plug your Ethernet into it, so you have to have an Ethernet port too. And that's the only way you can control your robot once you're at the driver station, once you're in the field. I have a Dell Inspiron that I got, I think, sophomore year or maybe freshman year. It's missing some screws and a few pieces of the body. It's got like a chip where a gear fell on it on the screen, and for the longest time some keys on the keyboard would randomly like stop working, but I mean, it worked. I still got even the 254 sticker, the last one they were giving out back at Worlds, I think. Yeah, it had to have been. It's never coming off, obviously. I also got a Rockbot sticker. Hey guys. Anyway, you should really invest in good memory with these and avoid stuffing too much stuff in its storage, since it'll slow down. And you definitely don't want to have it run slowly, especially during those moments where like every second counts. Battery life, that's a killer too. Watch out for it, especially since I don't recall them having power strips in the driver area for you to plug into. So like every time you're not in the match, you have to be charging them. And these competition days, they go on for a while, so like you have to watch out, seriously. The next piece of technology, that's the Robo Rio. It's this gray box. It doesn't look like much. It looks like some old piece of tech from the 90s, but it's actually pretty it's pretty advanced, I think. At least in terms of FRC programming stuff, compared to what came before it. Yeah. This is the central computer for the robot that uses to move its parts and things in accordance to your program. Don't get anything in those ports. Don't get any dust or water or anything. These things are expensive. Seriously. Even though they give you like a big discount if you're like an actual team, it's still... We have multiple, and I'm pretty sure half of the ones we have are like busted for one reason or another. If you don't have a Robo Rio, and by extension a radio to communicate with the robot wirelessly, you don't have a robot. So let's talk about the process. What's a programmer going to be doing over the course of the season? Well, aside from researching, which you should always be doing, the process kind of looks like this. You code as the team builds the robot. It's important to start working on your programs as the robot's being built so that you can start testing as soon as possible. Literally, the instant they give you the robot, you got to be off to the races when it comes to autonomous, teleop, everything. This way, you're also able to communicate with the engineers as they're building, so you have a better idea of what to program around. Next is deploying your code that you finish up, and then testing it. Then inevitably something breaks and you have to go back to square one, both engineers and programmers. Hopefully this happens enough times that by the time you get to competition day, your robot will be a well-iterated, well-oiled machine, and both you and the drive team will have slept well since y'all didn't spend the entire night before doing last-minute fixes, right? I hope so. Right, okay, we get it. We know what programmers do. But I've been picked as a programmer, and now I'm staring at google.com at a blank screen. What do I do? How do I learn how to code in plain English? Boom. The FRC Control System website. These are the sacred texts, the bread and butter, the enchiridion, the resource with the most source, the website with insight, the tome of tidings, the words of wisdom, the WPI library. I don't know what WPI stands for. That's up to you to find out. When I first started FRC programming, the veteran at the time told me to read through it all, no exceptions. Multiple times if I had to, watching some supplementary videos if any were available. I'm just a chump with 2 years of genuine FRC programming experience under my belt. That is what you should really be studying up on, the WPI libraries. The link is right above the picture. I suggest you go there. If you can't see it, I'll do whatever it takes to make sure that when this becomes a video, or if it becomes a video, that link is included, because that's what you need. It not only tells you how to set up the software you need to program and deploy code, it also tells you about things like LabVIEW wiring, even engineering. If you want to learn how to program a sensor, you refer to the website. If you want to see an example program, you go to that website. You want to know how to use cameras or a smart dashboard or anything, the WPI library, the FRC Control System website, that's where you go every single time. I mean, I'm still going to talk about at least a couple of those things anyway, since I got 50 minutes to fill, but still, this is the place to be. But if you're having trouble implementing what you learned, what if the language of the website is maybe a little bit too tough to read at first? What if you have a question that your mentor may not know the answer to? You don't give up. Not at all. The most important thing I've learned from my time in robotics is that the solution is out there. And if you're willing to spend the time searching for it, you will find it. And where will you find it? Boom. Chief Delphi. The WPI library and Chief Delphi are the 1-2 punch of FRC programming, with YouTube guides being the occasional third jab. This forum has been around, I think, since 2001. That's older than me. And it's been the place where people have had their questions be answered since then. And it's been the place where people have had their questions just answered since 2001. Years, decades. There's literally no problem that I've ever had programming, engineering, anything that hasn't been answered on Chief Delphi like 5 years ago. It's nuts. You might not find the easy answer immediately. You may have to decode someone else's program and learn how to do what they're doing in like your own way, or you have to figure out what exactly they're talking about, since most posts are years old and you might not get a reply if you ask for clarification. But I think that's the fun of it. I think Chief Delphi is one of those sources that teaches you one of the most important skills you can learn in robotics. Searching for things that can help you and understanding and piecing together the facts. I mean, it's a jungle in there, and it may take you 10 or more tangentially related posts before you find that critical piece of information you need to solve your problem. But once you do, man, you're on top of the world. But let's go over the layout. So you understand some more stuff about programming. But what are we actually programming on? This is a nice example of what your wiring board might look like. Thanks a bunch to Aluminum Narwhals for posting this on Chief Delphi. This is the Roborio, and this is a USB-B port, the same kind most printers use. Funny story, we would actually, in order to save on buying another USB-B cord, we would swap out the one we were using for our 3D printer every time we needed to test something, and vice versa. And this is the radio. We use this to communicate wirelessly, you know that. What I want to talk about are these boxes surrounding the giant power distribution module. These are called motor controllers, and there are many different types, such as Spark, Victors, Talons. They're basically like different brands. Every motor has a wire that you screw into these motor controllers to give them power. Notice that black, white, and red PWM wire. That goes all the way back to the Roborio. That's because that PWM wire is what tells the motor what to do according to the program. Therefore, in order to know which motor is what, you need to be able to know which motor goes to which PWM port, which port number is it. You wouldn't want your front left and your back right motor to be swapped around, right? Trust me, you don't. Make sure your engineers wire neatly so you can tell, or at least Sharpie the port number onto a piece of tape, stick it on the motor. That's what we did. Anyway, I know what you're all here for. Let's get into it. Let's talk about robot.java. Once you finally get through all the blah 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 in the setup, you're left with this program. I'm viewing this on GitHub because this is actually where my veteran mentor guy would have it online, so that we would be able to take it onto our computer and then edit it and then put it back on GitHub. So this way it's always there for me to look at, and I'm looking at it right now. So this is it, robot.java. It's an open canvas, and you're Jackson Pollock after a rough day. If you're new, it's going to look disgusting by the time you're done with it, but it's yours, and your team's, of course. What we're looking at is the exact program we used way back in Power Up, and we've basically been reusing its skeleton ever since. It's pretty macabre when you think about it that way, but I mean, it's time efficient, you know what I'm saying? These programs, called classes, follow a particular structure. There are different types, but this is the one that we like to run. In our case, it starts by creating itself along with some other things. Then it has this initialization period, and then another one for auto specifically, and then the actual autonomous code. Then, the TeleOp initializes, and then it's the TeleOp code. And the TeleOp code runs non-stop until, you turn the robot off or you turn the program off. And then there's also like this practice section that you can select in the driver station. It's just another TeleOp, but you can try stuff out there without ruining your actual TeleOp program. So let's just go down the list and see what each part of the program brings and what info we put in it. So this is the imports. This is basically how every Java and C++ program starts. It begins by declaring its package, that is, where it is. It's actually saying where it is inside the files of your computer. In the same way your Steam folder might be within your program files folder, which is inside of your local disk. Our program is inside of a folder called Team3035, which is inside a folder called FRC, and so on. The same logic applies to the imports. These are the locations of other classes that have information that we use throughout the program. This class doesn't start off knowing what a gyro is or what a spark motor is, so we have to use information from those respective classes and then import them and then use that. As you use things from those classes, they'll probably automatically fill themselves in or say, hey, we don't know what this is, are you talking about this? And then it'll be like that class that they're talking about, and then you select that and it just fills itself in. After the imports are called, then the class declaration happens. That's what that public class robotics ends business is talking about. That's how we know that this program is called a robot. This is also the place where you can create more objects, which can be used later for real things like motors, or for abstract things like the different types of autonomous programs you can run. This is also where you would create the joystick object, which you would later need to control your robot during TeleOp. At override public void robot int. These are what you'll usually see. This basically defines when one section of the program ends and the next begins. You can consider this portion the pre-start, everything that you can make run before the game starts. From here you can create the object for the camera, link each motor to their motor controller. This is where those port numbers come into play. After you link them, you won't have to worry about remembering them anymore. You can just use the letter designations. I can't tell you much about autonomous in it, to be honest. We never experimented much with it, wanting to make the most out of our time and whatnot. You could probably use it to maybe turn on the limelight and blind everyone before the match even begins. After the game starts and you select auto on the driver station, or rather it picks itself, the autonomous periodic begins. The periodic means that this code will run non-stop until the 30 seconds have passed and the program ends itself. That means you should probably tell the motors to stop for a long time after your auto is done, so it doesn't start looping back around and start restarting itself. You might be confused by the switch and case stuff. That's a conditional, much like an if statement. However, we wanted to have a different auto for multiple different causalities that the fuel system would tell our robot. Instead of just making an incomprehensible webs of ifs and else ifs, we made this conditional to switch to the program depending on the case. Or rather, the case would be the program that we would use. And then having a default drive straight if none of the other cases are chosen for whatever reason. Autos, man. Probably the most important thing to do at the highest level, but a nightmare to finagle with at the lower levels without a lot of time. Here's a bunch of questions I'll probably ask myself in nightmares for the next couple decades. Oh man, we didn't tell it to stop. Did we? Did we tell it to stop or to start or what? Maybe a demon possessed it and compelled it to not to turn when I wanted it to, and now it's heading straight to the other side of the field. Better hit the emergency stop button. The robot won't be able to move for the rest of the match, but hey, you won't risk any more penalties. You'll also never hear the end of it from your teammates, but I mean that just comes with the territory. Don't worry about it. Maybe your robot really likes that one Pikachu meme and just won't stop spinning around. You won't be able to do anything else, just spins for 30 seconds straight. Maybe if you're lucky it won't break anything else, but let's be honest, it'll break something. You don't even know how the code thinks you want it to spin, it just does it. It's grooving, don't get me wrong, it's schmooves, but it's spinning a little fast, and did a wheel just come off? Yes, it did. amongst like 5 other snapped components and split wires since the bot just wanted to spin a little too fast. There are tons of factors that contribute to your robot breaking itself inside on the field. Power, static, hastily done wiring, screwing, maybe the auto busting a dangerous move in the middle of the match isn't a symptom of another problem, as opposed to a programming problem itself. However, the best way to know for sure is to continue testing it. If nothing else is affecting it, the program will make the robot do the same thing every single time. At least that's the hope, right? Here it is. The TeleOp periodic. It's like the autonomous periodic. It checks every conditional and joystick value every 250 milliseconds, I think. I remember that number because I was working on getting this button to toggle between 2 different things, and sometimes hitting it would work, and if I hit it really fast, it would work. But maybe it was stupid. Just remember to first, this time you can actually control the robot. That's what it is. Yeah, you can actually control the robot this time. Just remember to first make a speed, connect its value to how far you push the stick. These can be done at the same time, and then map that power to each of the motors. You might be wondering, what is raw axis 0 in relation to an Xbox style controller? I don't remember, to be honest. I'm serious. The only way to know which button and stick does what, you have to connect your controller to the computer and check each one on the driver station app. I had them all written down, but the notebook where I wrote it down is in my house about 200 miles away. Sorry. Luckily, past me made sure to leave helpful comments in the code so I wouldn't be lost looking at this. Comments are a great way for people to make their nonsense code intelligible to others that will look at it in the future, such as rookies. It's good practice to leave them near any ambiguous portion of code to clarify some things about it, such as its purpose. But dude, you might be asking, you've already forgotten my name. It's cool, don't worry about it. I don't care about the other stuff. How do I make the motors move? Well, let's look at the code I use for the intake system of my robot to find out. I cut out some of the extra controls we had to line things up better, but here it is. Step 1, link the gamepad controls to a speed. My driver wanted the left trigger to be the intake and the right trigger to reverse those motor powers and shoot the cube. Was it the right and left trigger actually? I don't remember. I should have read those comments. We have it like this. Since a trigger can only go from 0, which is unpressed, to 1, fully pressed, you could have the motor powers be on one stick, which can go from -1, fully down, to 1, fully up. But my drivers didn't find that comfortable. Anyway, the next step is to have some conditionals to check if the triggers are being held and for how long. It looks like this. We were pretty clever here. We made it so that the pressure held on the trigger was directly proportional to the power of the motor. So when the outtake trigger was pulled all the way, the outtake motors ran at full power. We limited the intake speed, however, by a factor of 0.44 since, pro tip, ultra fast spinning wheels, way worse at intaking big cubes than slow spinning ones. But what about driving the robot itself? Well, if you get a West Coast drivetrain, like I think comes with kit parts, there are usually 2 ways you can control your robot. You can have the left stick control the left wheels and the right stick control the right wheels. This is called tank drive. I don't know if actual tanks are driven like that, but I know a lot of video game tanks that do. Alternatively, you can have the left stick purely control forward and backward movement of all the motors, while tilting the right stick makes the robot turn. This is called arcade drive. Think of it like a video game, where the right stick controls the camera. FRC bots are pretty fast. I personally like how, with arcade drive, you can really confidently traverse the entire field at a good speed. That said, tank drive removes a lot of ambiguity of your control at low speeds, and when you can't tell which side of your robot is which. These are the powers that you have to put on your motors in order to make arcade drive work. Just take my word for it. Try experimenting with it to learn some new ways for your robot to look messed up. My driver actually liked using both for different purposes, So guess who had to work in the toggle button for them to switch control methods at will? Yeah, kind of awesome. But this is also kind of where the basic code instruction ends. That was a mouthful. Tell you what, before we go any further, let's take a bit of a breather and watch this video of my team competing in the finals of the district champions. One of our favorite things to do as a team before kickoff was to watch some of our match videos from the previous season. It felt really good to kick back and watch these in retrospect. In the meantime, if anyone has any questions in chat, this is a great time to ask.
We can get started. Let's see who wins Texas. Here we go. Space Explorers between the lines in 3, 2, 1, go.
The Blue Alliance looking to get that bread to stay alive. The Red Alliance needs a win to take it all. Barbecue poised and ready, looking to put another one up on the Barbie. Meanwhile, 148, 3310, rocketing back, hatch panels in tow, the Sandstorm about to clear up. 3035, that's Droid Rage, tucking a piece of cargo in for the Red Alliance. Black Hawk looking to fly to the sky. 1817's not having it. They're pushing Black Hawk back. Meanwhile, 148 scoring as fast as they can. Black Hawk still putting one down. Blue Alliance Barbecue having a bit of trouble there. Their intake stuck to the ground for now. Spectrum looking to show the Red Alliance the rainbow, looking to pick up a hatch panel and outscore them. 1817 waiting for Blackhawk. 148 looking to put a hatch panel down. Lining her up just right. And they get her done. 3310 rushing to the other side of the field. 1817 struggling to keep up. Spectrum tucking another one away for the Blue Alliance. Barbecue a little bit of trouble there, hoping to flip that cargo in to the cargo bay or to the Blue Alliance rocket. Droid Rage coming back with another piece of cargo for the Red Alliance. It goes up, it ricochets off their robot. 1817 hits them. That piece of cargo falls right out. Blackhawk and 148 both going after the Red Alliance rocket. 1817 slowing down those cycle times for the Red Alliance. Meanwhile, Droid Rage carefully puts another piece of cargo away. 148 follows as well. Meanwhile, Spectrum looking to get a hatch panel for that Blue Alliance. Barbecue having a bit of trouble. The meat is very rare. Blackhawk having a bit of trouble as well. 148 now coming to play some defense on Spectrum and Barbecue. The Wranglers looking to wrangle up the Blue Alliance. 1817 looking to raid the Red Alliance. Defense on defense, dog. 3035, Droid Rage trying to come back. 1817 playing some heavy defense. 148 playing some heavy defense. Oh, the Robo-Manity. 148 rushing back for a piece of cargo. 3035 looking to put a piece of cargo away. 3310 having a bit of trouble. Looks like they'll nest there for now. 148 tucking another one away. 3035 pushing them out of the way. 3310's back up and running. 1817 is at level 3. 148 is up. 3310 looking to go for that level 2. 3035 joining them. Barbecue is up as well. Spectrum looking for those last second half points. And that's how we'll close out the match.
What is that ref doing with his hands? I just realized that.
The winner for Texas District Champs is your Red Alliance. Please give a big round of applause to your number 3 seeded Blue Alliance, made up of 3847 Spectrum, 1817 the Llano Estacado Robo Raiders, and 2714 Barbecue.
Let's take a bit of a detour to demonstrate the learning process for a few things in programming. Let's say I want to program a servo. How do I do that? Well, step one, definitely look for it on the FRC control system, and hey, there it is. It takes you directly to a short document with, it's only 3 pieces of information. How to create a new one, servo, example servo equals new servo, and the port number. We're shown 2 different ways to make it move. Either setting it to a value between 0 and 1, representing the 2 different extremes the servo can go to, and an angle, which makes sense since a servo only turns a certain amount of degrees. It varies by servo, but still. And that's just that. But what about something like a gyro? That's a good question. For those unfamiliar, a gyroscope is a piece of technology that allows a robot to collect accurate information about its heading or its angle. You can use this information to know exactly how far to turn, but it may sound tough to do from scratch. So let's go over it step by step. This is a Navex gyro. This is actually the model that my team has used for a few seasons now. It may not look like much, you just stick it onto the Robo Rio, but its power can't be denied. It may not look like much. It comes with its own third-party software that you need to make play nice with the WPI library. But they actually provide a really nice guide on their own website that makes the whole process pretty simple. Once that's out of the way, you have a gyro to use, but we're not quite done yet. I mean, let's say we have a gyro set up and we use it. What's going to happen if the robot turns? It's not quite like with the very small FTC robots. When you make an FRC robot turn at set angle, it may not even be close to the angle you want by the time it stops. When you want consistent actions for, say, autonomous, that's a problem. The solution lies with PID loops. PID stands for Please Ignore Dastardly Acronyms. Essentially, a PID works like this. Say you want to turn 90 degrees to the left. The robot will try to turn to that angle like normal. It won't be close, but then it'll automatically turn a bit in the opposite direction to correct itself. And then it'll turn again to correct itself after that. Then it'll loop around. It'll keep doing that until it gets to the desired value, or rather, the difference between the desired value and the opposite, and the value that it's detecting is deemed close enough, or it runs out of allowed corrections, both of which you can alter in code. All of the information on this is included in the control system site and also elsewhere. Chief Delphi for sure probably has tons and tons of questions about something like that. So here's an example on how we can force a gyro turn in TeleOp. It's not shown here, but this whole thing that I'm showing is under the condition that a button is being held down. This is so we can end it as soon as we consider the turn complete. So let's break this down. Math.abs refers to the absolute value of something, which makes sense. This actually works really well for many people that are learning PEMDAS and whatnot, because that's exactly what's going on here. What this if statement is saying is that we will essentially stop the motors once the difference between the recorded angle value and the desired one is less than or equal to 3. And if it's not, move the motors. I don't remember which direction we have it turning, but if you think about how a negative angle is counterclockwise, you can probably infer that information and then use that to change the direction of the turn in order to make the turn faster. That's essentially it for gyros. Of course not. It's not the only thing about gyros, but that's essentially the extent to which we used it in our team. Just simply turning in autonomous and having a dandy little optional toy to mess around with in TeleOp. I am most certainly not the most qualified guy to tell the World Wide Web how they should be coding. I'm sure 1678, Citrus Circuits, and many other wonderful teams out there probably have more than enough material out there for you to sink your teeth into if you want to learn the truly the best way to program. I chose to present this more from the standpoint of a kid who had to program for their poor mentorless team when no one else would. when our continued support from our sponsors and schools depended on our performance, with no resources at our disposal aside from whatever we can find from the internet and each other. That said, I think we did pretty alright for ourselves. Under these circumstances, everyone has no choice but to wear multiple hats, working on multiple different things and jobs at once. You have to prioritize what's important and within your ability and schedule when you're programming. These are the most important things that I needed to know. There's more, of course: encoders, gyros, PID loops, computer vision, troubleshooting. Gosh, troubleshooting. But, you know, if you're just starting out and you've got to make do with what you got, you'd be surprised how far you can get with a robot with a little arm that drives good. Thank you for watching. Stick around after this short break. We'll pick up with some more advanced pro tip programmer hacks and unauthorized guides at 2. See ya.
This concludes this session. If you're watching us live, please take the time to go back to YouTube and pick up our next session, or you can always visit our live page at firstrgv.me/live and pick up the next session there. We appreciate you watching and participating in today's session.